All right, so what I want to talk about in this video is using the integral form of the center of mass equation. So far, we've just used the center of mass formula like this, that if I want to find the center of mass, it's the average position of all the mass in the object. So I'm just going to take each little bit of mass in my object and multiply by its position, and add all those up, and then just divide by the sum of all the mass in the object, so by the total mass. Well, you say this works fine if I have a bunch of separate discrete masses at specific positions, and I can add them all up. But if I have an extended object, like a cylinder or a disk or some other solid object, and I want to find the center of mass of it, well, if it happens to be a pretty simple symmetric shape, it's usually not too bad to find the center of mass. And what we're doing then is we're just going to take that object, and instead of having a bunch of separate discrete masses, we're just going to add up an infinite number of little dm's, split into an infinite number of little pieces, and add up each little piece times its position, and add them up until we've added up the total mass, big M, of the object. And divide by that total mass of the object. And so that's just using an integral form of the center of mass equation. And so that's the idea. I want to show you using an example. What makes this integral weird is that I'm taking an integral with respect to mass, which is unusual, and then I notice that I need to multiply each little tiny little infinitesimally small bit of mass times its position. Well, that's typically going to be two variables. And so if I have two separate variables, that's a problem with integrals. You see, I need to have everything in terms of just one variable, the variable of integration. So I need to either rewrite the positions in terms of mass, which again, taking integrals respect to mass is unusual, not at all what we're comfortable with, or rewrite mass in terms of position, or I suppose rewrite both of them in terms of some third variable that I can integrate. So that's the plan. So in a way, this is a very mathematical sort of video I'm making here. I'm talking you through basically this process of changing the variable of integration and how we apply that to finding the center of mass. This same process we can use for finding the total mass in an object, or we can use it for finding the moment of inertia in the rotation unit, or we can use it down the road for finding gravitational field strength from an extended body, or the same sort of technique for finding electrical field strength from a distribution of charge, or finding the total charge in an object, or so on. And so this is a really useful mathematical thing, changing the variable of integration, that we're going to show you today. So moving on, let's start with an example here. I think what I want to do for my first example is I'm going to use finding the center of mass from a uniform rod. Okay, so let's say that they give us a picture, and they say, hey, here is this, and for our first example, of this long, thin rod, we're going to say, hey, this is a uniform rod, so the mass is spread evenly through it for our first example. You say, hey, if I've got a uniform rod, let's see here, then you say, hey, I can figure out where the center of mass is. It'll be symmetric. It'll be right in the middle. But let's go ahead and use this, an example where we know what the answer is going to come out to be, to check the procedure and figure out how we're going to do this for more complicated cases. Say uniform rod of, and we'll we'll even tell you the total mass is big M, and say the total length is a little cursive L there, and we're going to say, hey, let's just find the center of mass. Okay, and so you say, well, I don't have a bunch of separate discrete particles that I can add up their positions of. I'm going to take this and split up in an infinite number of little bits and use the integral form. And so given this information, typically what I'll do is I'll go ahead and let's see here, let's drop a coordinate axis down on the world. I'm going to run an axis along the length. Let's go ahead and call this spot x equals 0. Then you say, hey, that means this spot must be x equals L, right? And what I'm going to do is I'm going to take this, and our formula says that we want to do to find the center of mass is we want to take the sum of all the little bits of mass times their positions until I've added up from m equals 0 to m equals big M, all the mass in the object, right? And so I'm going to slice it up, slice, 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 slice. Slice, 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 into an infinite number of little dm's. So each one of these pieces, each one of these little pieces has a mass dm, and each one of these little pieces, you would agree, has a width here that I guess would be dx on this x-axis. All right. So what we're going to do is we're going to say, hey, this is the integral we want to take. And you say, the problem is that I've got two variables, right? I've got this m and this x. And as I go from little bit to little bit, the x is changing. As I go from little dm to dm, as the m is changing, as I say, hey, that's two variables. And so what we're going to do is we're going to change the variable of integration. So I need this to be in terms of just one variable, not two. So here's the trick we're going to use. We're going to use a relationship between the mass and length. You say if this is a uniform rod, then if I were to take, say, the whole rod, I'd say it's got a certain mass, and I take the total length L. You say, but if I took half the length, wouldn't it have half the mass? Or if I took a fourth of the length, wouldn't it have a fourth of the mass? You say if this is uniform, that's going to be the case. Or if I took a little dl of length, it would have a little dm of mass. And so that ratio, my mass to length ratio, we're going to call that the linear mass density. Now, when we talk about density, you say, hey, I remember in chemistry learning about density, and back then they said that density was the mass divided by the volume. Now, I'm going to abbreviate volume VOL for my own reasons instead of just V. And you say back in chem, they would have told you, hey, D for density. But physicists tend to use the Greek letter rho. So here's a lowercase rho. And this is called the volumetric mass density. This is what you're used to when you think of density. It's my mass per volume, being like kilograms per cubic meter. In chem, you probably did things like grams per cubic centimeter, but whatever, same idea. You say, well, we can also think about if I had some sort of material, uniform material. I don't have anything handy to use. Sure. You say, maybe I have this chunk of paper. And you say, hey, if I were to take and just cut out, like punch through this thing a square centimeter, you say it would have a certain mass. If I punch through a square centimeter from over here, it would have that same mass, right? And punch through. I could talk about the mass per square centimeter that I punch out, right? I could talk about mass per area punched through this this chunk, right? And that'd be to give me the density of this, what we call the surface mass density. So surface mass density is my density per my mass per area punched through the object. It's a surface mass density, so we're going to use like a Greek letter S, a sigma. We're going to use a lowercase sigma, okay? And that looks kind of like this. It's kind of like a O that doesn't quite close on itself and kind of loops like that. That's lowercase sigma. This is my mass per area, right? That's my surface mass density. I'm thinking that as being my mass per area that I punch through an object. What we're going to do in this case, we're going to talk about mass per length, right? And this is called my linear mass density. And so, because it's linear per length, we're going to use a Greek letter L. We're going to use a lowercase lambda. Okay, and that looks like that guy. So if lambda is the ratio of the mass to the length, which for this thing, because it's uniform, the mass to length is the same everywhere through it, I'd have the same answer, same ratio. If I took half the mass, it would be half the length, or a fourth of the mass, fourth length, or more importantly for us, if I took a little dm to d length, that'll be the same ratio. Now for us, a little bit of length is the same thing as dx, a little bit along the x-axis. So this is actually the same thing as dl. And so I can rearrange this and say, just like I'd say, dm is going to be lambda d length. I could also say that it's going to be lambda dx. Okay, and that's actually the form I'm going to use to substitute in here for dm. So these are some ideas we might use in different problems depending on the geometry we're working with. My volumetric mass density, surface mass density, or linear mass density. We're going to use linear for this case for a rod. Go figure. So let's go ahead and do that. We're going to substitute lambda dx in where it says dm. And so my equation, as I track down, is going to look like this. And I'm going to integrate. We have x. Now where it said dm, we're subbing in lambda dx. And so now something you got to be careful about is when you change the variable of integration, you say, well, I was adding up the position times each little bit of mass, and I was going to do that as I added up, add, slice, from one end to the other until I've added up to the total mass from little m is 0 to little m is big M. That was my integration, but now my variable changed. So I need to make the bounds of my integral be in terms of the new variable. But it still has to be the same integral I was doing before. I still have to be adding up to get the whole rod. And so my bounds are going to be new bounds in terms of my new variable x, but they got to correspond to the old bounds, right? So my new bounds for my integral they have to be in terms of the new variable. Okay, but correspond to the old bounds. So we're still doing the same integral. We're still adding up this whole thing. You say, but now my new bounds, you say, well, I was going from here, slice, till I had all the mass. Well, we're going to go from x equals 0 to x equals L. So I'm changing my bounds to be in terms of my new variable, but still correspond with the old bounds were. Okay, that's it. All right, so this is kind of the setup so far. What you do now is, now you say, hey, is this something I can take the integral of? You say, well, lambda in this case, lambda, it turns out, you say, hey, that's a constant, right? It's in terms of m and l, and those were constants I was given. And so I can just go ahead and factor that lambda right out of the integral, right? Constants you can factor out. And so my center of mass, move that lambda right out. And so I say, hey, clearly now that's just x dx. And you say, hey, that's an integral I can take. You say, hey, the integral of x dx, that's going to be a 1/2 x squared, right? I'm going to go ahead and I'm going to evaluate that from x equals 0 to x equals L. All right. And I still have this lambda and this 1/m
hanging around out front. And so continuing on, you would say, yeah, sure. When I put in the L, it's just going to be 1/2 L squared. Put in the 0, it's just going to be 0. So it's just 1/2 L squared. So my center of mass is going to be 1 over m lambda 1. 1/2 L squared, right? And you say, okay, great. Am I done? And you say, well, no, because lambda, that was a variable that we invented. Okay, lambda was not given to us in the problem. We were given just m and l. So I need to go ahead and rewrite, get rid of the lambda. So since lambda is equal to m over l, I'll just swap m over l back in for lambda, and I'll have this in terms of what I was given. So again, we'll stick in just that m over l for that lambda. And now, wonderful things happen. You say, hey, this m is going to cancel that m, and one of these l's is going to cancel that l. And you say, hey, what's left? What's left is just 1/2 L. And you say, hey, sure enough, that is what we knew. We knew the center of mass had to be at 1/2 L, right? It had to be right in the middle. This was nice and symmetric, right? And so sure enough, this process gives us that answer, which is what we would expect. Okay, so that is just an example of using the linear mass density, right, to change the variable of integration so that we can solve using the integral form of the center of mass equation. So what I want to do next, I want to go ahead and show you a case that's not quite so simple. So just like kind of one step more challenging, and that's what if the mass was not uniformly distributed? And so they, instead of telling us the total mass, giving a variable m, instead they just tell us the density as a function of length. The example I was talking about in class is if I took a hollow tube and I took it out and put it in the snow and scooped up a bunch of snow, and then maybe took that tube and thumped it on the ground, well, the snow would be more densely packed at what was the bottom when I thumped it, and less densely packed at this end. So I get more dense as I moved along the rod, along the tube there. They say that would be a more interesting problem to take a look at. And so I think I'm going to do that in a second video.